Alright, good morning. And next week we are having our midterm, okay? And I'll let you know, like on Monday or Tuesday, I will let you know which classroom to use and where are you going to, because we totally will have about 100%, not 100%, sorry, 100 students. And we are not going to use this classroom to have your exam, and so maybe on the third floor, and I will let you know which classroom you should go. Okay? And last week we've gone through this slide. We are talking about global king, global maximum or global minimum, and local maximum, local minimum. It's actually absolute or relative, okay? So, should everyone be happy with this? Is that okay? And we've talked about this, so I suppose all of you have already known what is necessary and what is sufficient condition. Do you have any trouble with this one? Necessary condition or sufficient condition? Are you very clear with these two terms or not? Or not enough? Okay, let me give you some simple explanation. So you know, if P then Q, the statement. If you have a statement saying that if P then Q, you know this? We would say if P then Q. And it is equivalent as if not Q, then not P. Do you know this? Raise your hand if you know this, please. Just let me know. That many of you don't know this? Okay. So, if who did I say? Okay, if Simon is my son, then Simon must be a male, right? If Simon is not a male, then he could not be my son, right? So Q, we say Q is the necessary condition for P, which means without Q, we cannot have P, okay? So it is necessary. And we say P is the sufficient condition for Q. So if P is satisfied, then Q must be satisfied. P guarantees the occurrence of Q. Okay? So, alright, there is another thing, and I think it's worth mentioning here. And these two things hold at the same time, which means simultaneously. Okay? So if we say Q is the necessary condition for P, then we know it must be this. P is the sufficient condition for Q. It's the same thing because these two things are derived from the relationship this. Okay, from this statement, if P then Q. Whenever you see if P then Q, then we know two things. Q is the necessary condition, P is the sufficient condition. Alright? And sometimes you will see if P then Q, and you also see if Q then P, then we would say P and Q are necessary and sufficient condition for each other. Okay? So in Chinese, is 必要条件 is 充分条件. And necessary and sufficient, we will say, is 充要. Okay? So, let me give you an example. We say a number x is even, which means then x can be divided by 2 perfectly without any residual. Okay? So if x is even, then x can be divided by 2. On the contrary, when x can be divided by 2, then x must be even, right? So they are necessary for each other and sufficient for each other. So we call them as necessary and sufficient condition. Okay? Now, last week we talked about x star to be a local extreme. We're talking when the function f is differentiable, which means the function looks like this. Not like this, not like this, because at this point it is not differentiable, okay? It's not differentiable because the slope is discontinuous. Okay, the slope discontinuous. And you feel a kink. So whenever we have a smooth shape of a function, very smooth, you can just touch it and feel it is smoothing, okay? Then that kind of function, we call it differentiable. Whenever you feel something kinked, something very sharp, you feel uncomfortable, then it is undifferentiable. Okay? So with a differentiable function, and we want to say a local extreme value, be it maximum or minimum, at a point x star. So this condition, first order condition, must be met, must be satisfied. So because either maximum, the slope is 0, and minimum, the slope is 0, right? So the first condition means the point's slope. First order differentiation denotes or represents the slope, okay? And we say this condition is just necessary. It's just necessary, not sufficient. Because we have this relationship, okay? If x star is a relative extreme, then it must have a 0 slope. But with a 0 slope, the point can be maximum or minimum or an inflection point, okay? Remember the example I gave you, or like this, inflection point, 反曲点, okay? But an inflection point, the inflection point whose slope is not necessarily to be flat, to be 0, okay? It can be like a negative slope or positive slope for inflection point. So some points, some inflection points, whose slope is 0, but some may be positive or negative. So this relationship is okay, but in this direction, it is not. And so we can have this conclusion with a 0 slope. It is not necessary to be it doesn't guarantee a relative extreme. It doesn't guarantee this. Okay, you cannot be assured that a zero slope corresponds to a relative extreme because the possibility of the existence of inflection points, right? So we use the first order condition. We utilize the first order condition as a first step screening tool. We try to screen which points can be the candidates of a relative extremum. It's just a necessary condition, and we use it like a screening tool. You know screening tool? So if there are numerous candidates and we use the first order condition, we can just block a lot of weight, right? They can never, because they do not have a zero slope, so they can never be maximum or minimum. But with a zero slope, the point can be a maximum or minimum or an inflection point. Then we need another tool to decide which one they correspond to. Is that clear? All right. So, okay, this is the new one. It's just some terms. If f prime of x star is 0, which means the first order condition, so for either maximum, minimum, or inflection points, we code x star. So please correspond to here and denote it x star. X star here. X star. We call this x star as a critical value. So we want to find critical values and then check it corresponds to a maximum or minimum or inflection point. So the first thing, we need to find the critical value. And how can we find the critical values? Just use the first order condition. Okay? Utilize the first order condition, then we can find critical values. And the function value of the critical values, we call them as stationary values. So this is a stationary value, this is a stationary value, and this is a stationary value. They are denoted as f of x star. And you see a coordinate with x star, f of x star. So this is a point, right? And we call them stationary points. So this is a stationary point, a stationary point, stationary point. I lost my pen somewhere last weekend because I went to a meeting and I took it out, forgot to put it back to my bag. All right. Once again, critical value, critical value, stationary values, and stationary points. All right. I decide for this semester to skip this slide and just want to know. All you need to know are two terms, concave and convex. So this we call it convex, and this would be concave. And the trick, I remember these two terms. I myself V convex, so it's convex, and concave, so look like this. This is my cheek. And I think quite useful. I can remember it for decades. Because this slide a little bit complex, so I decided to skip it and leave this slide to the, if you want to learn this, go to the mathematical economics, okay, taught by Hodge. And also I already recommend to you my video clips on YouTube last week. And although it's 10 years ago, but I think it is still useful. But no English version, because at that time I just have a Chinese version, and that's just for fun for me, because that was the last year I taught mathematical economics. So don't come to me and make some request that, would you please just take another video in English? No, thank you. All right, let's have a look at this example. We have R, the function R and C corresponds to revenue and cost. R is revenue and C is cost. So we have the total revenue function R, which is 1200Q minus 2Q squared. And the cost would be Q cubic minus 61.25Q squared plus blah 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 blah, okay? And so with total revenue, with total cost, and we take the difference, then we will have pi, which is profit. So the profit function, pi, is just the difference of the two functions. And we have the profit function like this. So if you are a firm, you want to pursue a maximum of profit or minimum of profit. Hello guys, you are economics students? You want to maximize the profit, right? So we want to find the maximum, or we want to find out the quantity Q, which leads to a maximum profit. Okay, then how can we do that? The first step, of course, differentiate pi with respect to Q. So we are looking for the slope of the profit function, which will be minus 3Q squared plus 118.5Q minus, okay, and this 2000 in the cost function, the 2000, we call that a total fixed cost, right? Because it doesn't vary with quantity. So please make a note here. The term 2000 is a total fixed cost. And the first three terms consist of a total variable cost. the total variable cost consists of the first three terms, and the last one is total fixed cost. Okay? Alright, so you see with the first order condition, the total fixed cost doesn't mean anything. And we want the slope to be 0 because we want to apply the first order condition. Okay? And you may do something like this. Minus 3, Q minus 3, Q minus 3, 36.5. Okay? So, what kind of X star? Or we want to find the critical values of this function. What would be the critical values? Q star can be 3 or 36.5, is that right? So 3 can be a maximum, minimum, or inflection point. 36.5 can be a maximum, minimum, or inflection point. And we wanted to make sure which one corresponds to which one. And how can we do that? We just apply the second order condition. Do you remember that? Second order condition. When the second order condition is positive, it looks like a concave function, okay? If the second order condition is negative, then it looks like, what did I say? Positive is a convex function. And with a negative second order condition, there will be concave, okay? So, let's check the second order condition. We differentiate pi with respect to q twice. So this is the first differentiation, and then minus 6q plus 118.5. This would be the second order condition, right? So f double prime of 3 would be 100.5 is positive. And 36.5 would be am I right? 290? No? Oh, minus, plus, right? So it would be negative 100.5. Anything wrong? I'm right? Okay? So this would be negative. So now we know with the negative second order condition, it must be a maximum. So we have the answer, the maximum. And what about 3? A positive second order condition makes it to be a minimum. Okay? So we know if you are firm, then the best solution, the optimal solution to produce would be when the quantity is 36.5. Is that clear?
Why the minimum happens when Q equals to 3? I just don't understand. Since that we got second oh.
It's a vector decomposition. So everyone happy with this? just see something like this. With one variable, the function is a one variable function. So we can easily make the two-dimensional diagram to understand it. But if the function, if for a function there are two variables in the function, two arguments. So a two-argument function, like y equals f of x1 and x2, then the shape would be a 3D shape, okay? So with the domain x1 and x2, and we have a function value, axis. So now we have two x-axis and one y-axis. So something can be like this, or like this. This would be a maximum, right? It's a maximum. And if you turn the U shape into the inverse U into U, then it would be minimum. Okay? So for this case, you will see the slope along the x1 axis would be 0. And along the x2 axis would be 0, which means f1, this would be f1. So please say something here. f1 equals 0. And denote here f2 equals 0. So f1, which means the partial, f1 is, now y is f of x1 and x2. And we denote, or we define f1 as the partial f partial x1, or partial y partial x1. And you should, all of you should know why I use partial, right? And f2 is partial y, partial x2. So f1 is actually a slope along the x1 axis. So this is f1. And it's flat, it's horizontal. So it's f1 value equals 0. f1 equals 0, f2 equals 0 corresponds to a maximum. But this condition, now these two first order conditions, does not necessarily lead to this one, right? Because there are other possibilities like this. We call this as a saddle point. In Chinese, it is, okay, saddle point. So you see the saddle point. Along x1 is a minimum, and along x2 it is a maximum. Minimum and maximum. So this is just like a saddle, right? We can put the saddle on the back of the horse and ride a horse, right? For riding. So you see there, when for the red point, the slope f1 along the x1 axis is 0, and f2 is also 0. And this is actually a 3D inflection point. Okay? It's inflection along x2, inflection along x1. So the red point, we call it stationary point, right? Stationary point, stationary point, stationary point, stationary point.